Okay, so the next topic is T.C. Hope's experiment for the anomalous expansion of water. And T.C. Hope. Okay, who was T.C. Hope? T.C. Hope was a scientist who worked in the who worked in Europe. His full name was Thomas Charles Hope. He did this experiment in 1805. So let's see the apparatus what he used. This is a glass beaker, or even you can take a metallic cylinder, and this is dry ice. Here he used it for cooling. This is our thermometer 1 and thermometer 2, and this is fully filled with water. So here what he did was he just put this dry ice like a cylinder rack in the middle of the beaker or the cylinder. Then what happened was that initially both the thermometers, thermometer 1 and thermometer 2 at room temperature, the IR is initial reading. So the initial reading or first reading was at room temperature, and next the temperature recorded by the lower thermometer starts decreasing, and finally it settles down at 4 degrees Celsius. That is the final reading, 4 degrees Celsius. While the upper thermometer T1's temperature almost remains unchanged. It remains at room temperature itself. And after that, when the temperature recorded by the lower thermometer remains steady at 4 degrees Celsius, here 4 degrees Celsius, at that time this thermometer begins to show a drastic fall in temperature, and then it settles down at 0 degrees Celsius. So what happens is, initially if we have the room temperature at say we have the room temperature of water at 25 degrees Celsius, what happens is, first this water gets cooled down and it sinks to the bottom. So that is why the thermometer 2's temperature falls to 4 degrees Celsius. And then after, by convection, water of the cold water sinks to the bottom, and warm water here rises to the top. So when this also gets cooled, the density also falls rapidly, and this continues that till the temperature of the water reaches below the central portion. This is shown by the part here. Okay, and next, on further cooling below, the water expands, and so this becomes ice at 0 degrees Celsius. And then we can see that in the end, the lower thermometer 2, it shows the final reading of 4 degrees Celsius, while thermometer 1 shows the reading of 0 degrees Celsius. Okay, the next topic is consequences of anomalous expansion of water. Okay, let's see what the consequences of anomalous expansion of water are in nature. It helps in preserving the aquatic life during winter. You know, when the temperature falls below 0 degrees Celsius, so assume this is a lake, then the top layer freezes, because of T.C. Hope's experiment with the anomalous expansion of water. The upper layer freezes, and since ice is an insulator, it does not allow the sun's rays which are coming to get here, and also it insulates this and providing a warm thick layer. So here if it's 4 degrees Celsius, then the fishes and other aquatic animals can survive. Okay, let's see the next one. It causes crop destruction during very cold nights. You know why it causes crop destruction during very cold nights? Because plants have a stalk, or in their stems they have water. When the temperature falls below 0 degrees Celsius, they expand, and so the crop or the plant gets destroyed because it cannot withstand the expansion of the water in a fixed space. Next, it causes bursting of pipes in the winter season of cold climate countries. So here you can see this is ice cubes, and this is a pipe. Imagine if this is a closed pipe, here it's closed, and then you have the temperature like we have the temperature like minus 18 degrees Celsius, or you take even minus 4 degrees Celsius. At that time, water freezes and it expands. So when this is blocked, it tries to expand beyond this, and so it breaks this open. So that's why it causes the bursting of pipes in the winter season only of cold climate countries. It does not happen in areas near the equator. Okay, let's go to the next topic. And friends, this next topic is energy flow and its importance. Okay, what is energy flow, you may ask? So energy flow is the flow of the energy which is created by producers or only green plants in the form of photosynthesis using the solar energy of the sun. If we take a normal ecosystem or the flow of energy and in a food chain, we can see that this is the nearest ratio. This is the nearest ratio of the food chains, how many calories are burned and how many are used up. So let's read it once. Producers produce at least 20,810 calories, in which they spend 11,977 calories in respiration, and when they are eaten by the primary consumers, they spend 5,465 calories for decaying. So here again, primary consumers get 3,368 calories, in which they spend for respiration 1,890 calories, and for decay they spend 1,095 calories, and at last when they are eaten, after they are eaten, they spend this amount for decaying. Next, after they are eaten, the secondary consumers get only 383 calories. So here afterwards, when they get 383 calories, they use up 316 calories for respiration and 46 calories for decaying after being eaten by the tertiary consumers. Tertiary consumers are the last members of a food chain. So here, if they get only 21 calories, they use 15 calories in respiration and 6 calories in decay. Producers, you may take here for producers, you may take them as green plants, while for primary consumers, they will be herbivores. After that, when they are eaten by secondary consumers, they are carnivores. And the tertiary consumers at last are carnivores, or we also can call them as apex predators. Apex predators means the top predators in a food chain. So because they are the last members, they have been given the name apex predators. Let's see the characteristics of this according to the law of conservation of energy. So always the linear flow of energy in an ecosystem. So then we can see that this energy flow is linear, which means it moves line by line by line until the end. So always we can say linear flow of energy in an ecosystem means that the energy flow in an ecosystem is always linear. That's the rule. And next is, energy is neither created nor destroyed in food chains, but can only be transformed from one form to another. Here, that means that the energy produced by the producers and passed on to the primary consumers, secondary consumers and tertiary consumers is neither created nor destroyed in food chains. So we can see that it can neither be created nor destroyed, but can only be transformed from one form to another. Here the solar energy is transformed into the chemical energy, and chemical energy is transformed to here. The chemical energy becomes chemical energy, it remains as a chemical energy, and again until the food chain, end of the food chain also, it remains as chemical energy in the form of calories. A part of energy is always transformed into heat or an unuseful form of energy. Okay, if we take for example uh, the sun. When the sun produces sunlight, only 2% or 0.2% of it is actually used for photosynthesis. The rest 99 or 98% is complete waste in the form of heat. So a part of energy is always transformed into heat or other unuseful form of energy. So if we take another example in common life, if we eat too much and if we don't do much exercise, then the carbohydrates or the fats in our body get converted into ATP molecules and they are stored. Okay, so let us go through the table once again at the last. Sun gives solar energy from which we do photosynthesis, and then the producers or the green plants make use of it, and they use it for respiration and decaying after being eaten by the primary consumers who are herbivores, and then the primary consumers also use the energy for decay and respiration after getting eaten by the secondary consumers. The secondary consumers are carnivores, small carnivores like weasels, rats, snakes, etc., and they also use it for respiration and decay as usual. And when they are eaten by the tertiary consumers or the apex predators, topmost carnivores, they use this energy for decay and for respiration also. So let us go through the laws once again. Energy is neither created nor destroyed in food chains but can only be transformed from one form to another, and a part of energy is always transformed into heat or unuseful form of energy. And always remember, the flow of energy in an ecosystem is linear.